First of all, I'd like to welcome everybody to our webinar. This is our sort of educational knowledge transfer opportunity to put some of our experience forward on field-based construction. And today we're going to cover some of the pitfalls, show you a few scenarios that we've come across during our many years of being involved in artificial field construction. My name's Eric O'Donnell. I'm the MD of Sports Labs. I've got about 40 plus years experience in construction and 30 plus years experience in field construction particularly. So I think I've seen a lot of different scenarios over the years, but every day is a school day when it comes to building artificial fields. So hopefully in the next sort of hour or so, we're going to be talking about artificial field-based construction, hopefully helping you to eventually make informed decisions about what sort of base to install and how to make sure it's to the highest standard. Before we get into the detailed stuff, if you've got any questions that you'd like to ask, there's a chat function available on Teams, so it'd be great if you could put your questions as we go through the presentation onto the chat function, and Neil will pick these up as we go along, and there'll be time enough at the end to perhaps go through some of the questions that we've got from the attendees. So today we're not going to talk about design particularly, because the design of an artificial field base really starts from the ground up, and yeah, I'm not getting much activity with my slide deck here, Neil, in terms of moving it. So obviously soils or subgrade have a massive influence over the design of the base itself, and what we're not going to do today is talk about all the different types of soil conditions you'll get in the different states. I mean, today we've got delegates from all over the world really, so globally we can't really deal with all the different soil types and that we would come across. So we're trying to avoid talking specifically about design, and we'll deal mainly with the base construction itself. Unless you've got tons of money and a site where you don't have to worry about the levels, then the subgrade and the soils that you're building your field on has got a significant bearing on what you'll subsequently superimpose on top of it. And we can't stress enough really, get to know your subgrades or your soils when you're designing your base. A recipe approach is a very, very risky approach at the end of the day, and we'd stress not to go down that route if you can possibly avoid it. So moving on, if you can move the slides on for me, please, thank you. So next one. So let's talk a wee bit about what a typical base construction looks like. Now there's many bases, and we'll come on to that in a minute, but this typically is you'd have a subgrade layer here, you'd have subbase superimposed on top of that, the thickness and the type of materials dependent on the subgrade that it's being founded on or the soils it's being founded on. Typically you have a levelling layer. You may even have an asphalt layer on top of that, depending on the type of facility that you're ultimately going to be engaged with. Sometimes there's a shock pad and then the grass is laid on top of that. And that's a very typical construction. We'll look at a wee bit more detail into the different types of base construction in a few minutes. Next slide, Neil. So what does the foundation of a pitch do? What is it doing for the actual artificial field itself? Next slide. We're looking at essentially load spreading. You can see a couple of graphics here where, depending on the type of material that's superimposed over the subgrade being your soils, then you're looking to create a stiff beam of material which it doesn't flex doesn't settle, is permeable, and gives good load spreading. Now, you know, essentially we're not looking to load an artificial field significantly after it's been built, but sometimes you need a good base just to build the field. So if you're given a site which has got some issues with the either soft materials, or it may be reclaimed materials, or it may even be an old tip, then you need to put a decent base in to even get the field built in the first place, just to support construction traffic. So the base can be, it can be there for many, many reasons. Next slide. What does the base need to provide for a successful artificial field? Next slide, thank you. So as I said earlier on, there's different types of bases, and we've just grouped them into two types for this presentation. There's, depending on where you are and where your geography, what soil types you've got, there are a group of bases which are impermeable. So you're looking at designing a fall or slopes that allow the field to drain to the sides, to be collected in cut-off drains around the perimeter. Sometimes these fields will have shock pads which are actually drainage layers, so they de-water the runoff. It drains vertically into the shock pad and then leaves the site via a fall again into a cut-off drain. And then we have a group which are vertically draining. So here you've got usually a fairly thick layer of crushed stone, could be sand, could be other materials, but generally it's crushed stone. And then what you're looking for the runoff to do is to vertically drain through the whole system, so the turf, pad, whatever else is above the subbase, through the subbase and into a network of drains, where it's then transported off to a perimeter drain or a cut-off drain to an outfall. And that's the kind of simple look at the types of bases that are available. Next slide, thank you. So essentially, what do we look for the base to provide? Now, there are industry standards for this. We're obviously looking for bearing capacity, we're looking for stiffness, we're looking for it to be a very stiff, solid basement scenario. We're looking for porosity. We're not really looking for any deformation in the surface. Next slide. Oh, I think we jumped two there. If you go back one. And we're looking for flatness as well. We want a very flat, level surface. Now, in various standards, there are minimum requirements for, say, stiffness or bearing capacity, and this can be measured a number of ways. We've called it stiffness here, but some of the engineers out there will be familiar with CBRs or density tests that are done on the surface. We've set a standard through, you know, many years of experience, where we want a subbase, a crushed stone subbase material to hit a certain target. 60 kilopascals is about 1250 pounds per square foot on a load. So we've set a standard for ourselves. If we were designers and we went out to check a base, we would be looking for it, the majority of the subbase platform, to hit that standard. Generally speaking, if you do hit soft spots, they can be fairly easily remediated whilst you're on site, whilst you're doing the testing, and that's a scenario we encourage. Porosity is very important when you're looking at vertically draining base setups. This is quite a massive drainage rate, but 24 inches an hour is typically in specifications. You'll see lesser numbers in some of the contract documents, but our philosophy is the subbase needs to drain really well if it's going to be a porous subbase, because you've got many layers above that. You could have asphalt, you could have shock pads, sand, rubber, and then the pitch has got detritus in it eventually. So you're looking for the subbase to be draining at a significant rate when it's first installed. And for deformation, there's a number of ways of measuring this. We can use, you can use loaded trucks, or you can use a beam, but we're not looking for a lot of deflection in the subbase when it's been compacted and it's ready to be have the field installed. Next slide, if possible. Maybe not. Next slide, Neil. Flatness is very important, and you know, it's a requirement we often have problems with on a field, and there's a few different requirements depending on what the field's trying to do. So in soccer and rugby, which is heavily regulated, there's a requirement to have no gap greater than 10 millimeters under a 3 meters or 10-foot straight edge. It's pretty tight when you're looking at an infilled field with rubber crumb. It's not an easy measurement to make, but that's the regulation. Where you have an asphalt layer, and then maybe you're looking at field hockey, then it's even tighter. It's 6 mil under the same 10-foot straight edge, 1/4 of an inch. It's very, very tight, and you know, quite challenging for civil engineering. You know, using materials like stone and asphalt to get that tight tolerance. We have other local standards. The European standard is the same as the FIFA World Rugby, and then what you'll find maybe in some countries there'll be national governing body standards where they may offer a relaxed tolerance for surfaces that are starting to reach end of life or are starting to show wear and tear. So there'll be dispensation against these limits, and that might go for the performance testing on the actual artificial surface itself. The next slide. So what can go wrong now? Mark Corvas, the operations manager at Sports Labs, is going to talk a little bit more about this later on, actual scenarios, but very quickly, we have a few typical problems we see. The footprint in the levelling layer is not a good thing to see when you're trying to put a turf over a stone layer. These things do superimpose through the turf. And it does tell you a lot about the levelling layer. It may be too thick, it's probably too soft, it may be the wrong type of material. And similarly with dumper truck tracks, you know, you've just prepared a nice platform, it's flat, it's ready to have turf installed, and then the teleporter brings a roll of turf on and leaves tire tracks in it, which clearly have to be removed when you're laying the turf. See a lot of scenarios where there's been a poor choice of materials. So the materials itself, the slide there with the very, very uniform big stone, very difficult to level and very difficult to compact. So it's a very mobile material. It causes all sorts of problems when you're trying to lay turf over it because it moves around. You pull stones up, and it's just not a good material to try and finish the subbase off with. And then we see inadequate thickness. So what's happened there is subgrade is very up and down, bumpy, or they've just put a thin layer of subbase. This is about 6 or 7 inches thick, which is, you know, in that scenario wasn't thick enough. Next slide, please. And then you can see a few more here. So a couple of things just to pick up. We've got a nice shot of a material that looks perfectly fine on the left hand side. You scrape off the levelling layer and you can see you've got a very dense impermeable material, which is supposed to be vertically draining, and then when you do a test on it you can see a massive you know, pond of water forming around it, and it's just going nowhere. And you know, lay turf over that, you're going to have significant drainage issues when it's inclement weather. And then you've got another scenario there where the top layer is quite uniform, and then as you excavate down through the layer you get into fine materials, and eventually when you get to the bottom of the subbase layer, it's holding water on the subgrade, which will fill up eventually, and you could have another problem with drainage. So these are kind of things that we see when we're asked to come in and inspect or test subbase materials, and Mark, as I say, Mark will highlight some of these a little bit in a few minutes. Next slide, please. So just to underscore what I've just talked about there, we've seen examples of inadequate thickness of subbase, poor choice of materials. That's a significant issue. These materials are quite costly. There's always geography involved in crushed stone, so you're trying to buy locally. They might just not be the right type of material available. You're having to try and do the best job you can with the materials that are available, but it can have serious implications on the quality of the finish. If you're using a leveling layer, which normally if you've got an angular crushed rock, you will do, it's got to be compacted well into the surface of the subbase material, and it can't be too thick because you will leave marks in it. It will move around. It may even cause porosity issues itself. And then poor leveling of the final layers, that can be with roller marks, footprints, etc. That just makes the carpet installers, turf installers' life a misery. But other things like inadequate compaction of subbase on site, you don't want to see settlement after you've built a field. Poor handling of subbase can cause segregation, so you get this, what you saw earlier on, nice clean stone at the top, lots of fines at the bottom. Excessive trafficking of the final layer prior to laying turf, which as I say, leaves marks in the material and then causes problems for the installer. And then also the turf guys can cause a few problems with the plant. They bring the turf on site and maybe mishandle it a little bit, move it around a lot, and then you have problems where you have to roll in advance of the turf install, which is quite a difficult thing to do. Next slide, please. So at this point, I think it's good to have a look at some of the sites that we've been working on, and I'm going to hand over to Mark at this point, and he's going to talk a little bit about the problems he's seen on site and the testing that we do to try and mitigate or help to address these problems. So I'll hand over to Mark.
Hey everybody, my name is Mark Corvus. I've been with Sports Labs about 7 years now. So let's talk about some of the most common problems we see and why it's important to create build a good base. So inadequate drainage, that's one of the major first things here, which can cause flooding. An uneven surface at the finished layer, that's going to cause wavy lines, and then settling of the subbase. You'll see that on the surface as well. When the finished layer, turf layer goes down, you'll find rubber infills collected in those low spots. Most of the time you see any of these problems on the surface or on the finished layer, it's going to come back to the base. Occasionally it's an issue related to the surface materials, but honestly 9 times out of 10 it's going to be an issue that's come back to poor base construction. So here's a good example here of inadequate drainage. Massive flooding event. You can see this material's been pushed around, and then as well here there's pooling of water on the surface. These are things you don't want to see. They have major implications as far as playability going forward. So beginning with the playability here, yeah, I mean the purpose of installing some of these artificial turf fields, one of the major benefits is you can use them 24/7. If you've got a field that doesn't drain well, that's going to influence your ball interaction. You don't want to be splashing around on the field. And then special attention should be given to systems that utilize materials like cork, any light organic material. That's another thing to consider. That can be a major issue with flooding, and it's a different type of problem where these materials are going to move around a lot more than rubber. Just going back to here, you see the rubber more or less stays in one spot, and then here it moves around quite a bit. All right, so other things that can go wrong. Planarity. So you can see from this photo, the straight edge here is sitting on a ridge. And then beyond that, you have a lot of wavy lines in the back there. As well here, these lines, none of them look straight. Aesthetically, it can be a major problem. You have potentially, leaving track marks. This goes back to compaction, where we have what looks like tread marks, and I'm not sure if that's very visible in these photos. It's a little bit difficult to see, but we've all seen them in some cases where you have these ripples where that's potentially, it could be that the turf wasn't pulled tight enough, but it could also be, again, down to the base where we don't have a very compact base, and they've run a tractor along the top, and now we have these tread mark ripples in there. So back to these lines, your eyes are really good at noticing inconsistencies in lines that your brain knows should be straight. And so just even a slight difference in height, you're going to notice it. Earlier we mentioned, a 6 millimeter, 10 millimeter limit to planarity, which is, about a 1/4 inch or 3/8 inch. Doesn't sound like a lot, especially across, an 80,000 square foot surface or greater. But they do turn out to become pretty visible. All right, so once again, deviations within the base, they cause irregular lines. Another thing to note here, especially in the United States, a lot of fields now are being built with multiple sport lines. So you're going to have, 5 different sports, 3 different sports, whatever it might be. There's lines all over the place. So that can make the problem even worse. If you don't get the base right, then it's just going to be visible on the surface, and there's no real way around that. And then beyond that, even safety, your high and your lowest points, depending on the severity, they can be tripping hazards. We've seen some pretty extreme examples of that, where these low spots, running along, you got a 16 millimeter dip, or an inch dip there. It can be a tripping hazard. So why we use independent testing. So the GCs, installers, it protects everybody. You avoid upsetting owners and donors. We've all seen cases where, we have a problem on the field. You've got the GC who shows up on site. You've got the contractors. You've got the subcontractors, and then the owners and the donors, and they're all standing around pointing fingers. If you've got a major problem, and it gets messy, and beyond that, it can lead to things like litigation. It can lead to some major problems. And so to avoid that, it's best just to get the stuff checked off. It's not expensive for us to come in and do it. It's quick, and overall, it protects everybody in this case. So what can we do to prevent these problems? Infiltration testing. This is also called permeability. You might see it called porosity, depending on the spec that you're reading. There's a number of different names for it. All it is we're verifying that the base actually drains. And I know we talked earlier about bases that are designed to drain vertically, and bases that are designed to, shed water outwards towards sideline drains. There's different advantages to each type of test that we do, and I'm not going to go into the specifics of how the testing is done or our methods, but just so you're aware, we do have different tools that we can use. So we have our dual ring method, which really is focused on vertical drainage. It's got the advantage of isolating a small area on the field, and really it just focuses on does this surface drain vertically. Another advantage is, of course, we can isolate layer by layer. So say, of course, these bases are built with different layers. You might have, a cap layer of fines or finishing layer. We can verify that drains, and if that drains and we still have a drainage problem, then we can dig that part out and move on to the next layer, and really kind of in an investigation sort of see where the problem lies. And then even just beyond the base, we can do this at the surface as well and work our way down. Here's another photo of that. We also have the bucket test, or the non-confined test. This has the advantage of being a little more visually descriptive. So this is where we're flooding the field with 50 gallons and then 25 gallons, and you're able to see how fast this water moves across the surface, what direction it's moving. Ideally, it goes straight down and goes away. That doesn't always happen, and so just visually, it covers a lot more. In this photo here, you can see the area that it's moved out to. You can see standing water in certain areas. And then based on the area that it covers, how much water we've applied, we're able to calculate an inch per hour, a rough inch per hour drainage capacity for the field or the surface. Moving on to planarity, the way we check this, we've got a 3-meter bar that we drag across the field, and we cover every square inch of it. I know that there's other methods that are used, such as string line methods. Those work well, but we found that the best way really is just to get somebody behind this bar, and they're constantly looking at the bar, looking for high spots, low spots, and we're able to mark those locations, and hopefully and ideally we get them repaired as we're doing the test. And as I said, we've tried a ton of different ways of doing this. This just seems to be the best way, because we cover every single square inch of it. Here's an example of a report that we would put together. Pretty clearly, we're able to define where these deviations are. We can describe if it's due to an undulation, if it's a high spot, if it's a low spot. Other things we would of course note. We've even, I know this is a pretty basic looking one here. We've even been able to send a drone up, take a photo of the over top the field, and then download that photo, and then add in deviations and notes, very specific locations. Of course, that's for a field that's been installed, and then or a base perhaps that they're tearing up and reusing. We can do that as well. So accuracy is obviously really important, especially when we're coming back to fix things. Once again, ideally, as we go through the process of analyzing these bases for planarity, we'd like to have somebody on site there that can fix it as we go. It makes the process a lot smoother, and at the end of it, hopefully we can issue a report that doesn't have all this on there. It's just a nice clean report because we've fixed it that day. Here's a photo of the compaction testing as well. So say we find a problem and you've gone and installed the field anyways, or sorry, say you've gone and installed the field and haven't checked for issues. So now you've got to go back and fix these things. So the field has been installed, the turf is down, the infill is in there. Now we found the field is flooded. Now what do we do? To repair this, obviously it's very time consuming and very costly. It can involve removal and replacement of material. And again, this goes for, you know, whether the top layer has been installed or even before that. You might end up finding that you'll have to retrofit with additional drain systems. We've found several cases with this where perhaps the cap layer or the layer of the finishing layer is bound so tight that it was meant to drain vertically. It doesn't drain vertically. So now what do? Instead of ripping it up, and you know, you have a couple options here. You can remove all this material and replace it, or you know, it involves installing side drains, which means now you're digging up a field that's supposedly or supposed to be finished. And then you have all sorts of new problems where you've got to recheck for planarity, you've got to recheck for compaction, and in some of the worst cases, you know, fields that have been installed in sort of a drainage basin, it could involve installation of pumps, sump pumps, things like that. So it can get really messy real fast. And again, this can all be avoided by just having some simple testing done. And ideally, you know, that's how we go about it, is that we specify in that this testing is done beforehand and we can identify these problems before they happen. Planarity also, this is another really big one. With remedial work, it's really hard to fix it once the turf is down. You know, I spoke earlier about fixing the base as we go. That's the ideal way to do it. Because if you find that after that turf layer is down and you've got high spots, low spots, really the only way to fix it is to cut it open and cut open the field and then smooth it out. We've seen people try to roll it out, you know, with heavy rollers. That almost never works. We've seen them try to add infill, adding infill to bring up the level. All that leaves is a dark spot there. That doesn't help at all. And honestly, that goes back to the aesthetics. It just doesn't look good at the end either. So it's very hard to fix planarity issues after the fact. And then of course, you know, you've got to get a crew out there, and then it's the time that the field is not able to be used, and it becomes a major operation to have to fix this after the fact. So instead, we can spend a day, go through with the straight edge and find everything, fix it, and by the time we've done that, hopefully we've solved all the problems before they become a much larger problem at the very end. We've also started to see a lot of folks try to reuse their bases, E-layers. Of course, that's going to save a lot of money, but they should also be rechecked. Plenty of fields, you know, that have been in the ground for 10 years, they've got planarity issues. And you can see it on the surface too. You can already tell it's there. So we'll want to fix that. Also recheck the stability. Specifically E-layers, those can be damaged in the removal process. So even if you have one that looks good, as soon as you take the, once you take the turf off, you're driving heavy equipment around on it. Some of it's not very fragile. Some of the binders probably disintegrated a little bit, and these fields they'll tear up as you remove it. So even if you have the plan to reuse the base, the E layer, it needs to be rechecked. Here's a pretty extreme example where you've got splitting, and I think, you know, the forks from the removal equipment has probably jabbed the surface, and it's all sorts of torn up. So we're going to want to look at that as well. So I'm going to turn this back over to Eric now, where he'll talk about some of the other ways we can prevent this, and some of the ways that going back to laboratory testing, that we can utilize some tools.
Thanks, Mark. Maybe you could work the slide deck for me. I seem to have a slight technical issue on the slides. Thank you very much. So if you want to whip it on to the next slide. So so what we've been involved in over the years is like trying to look at the science of building bases. So this is just a scenario where we've created a large mold in the laboratory, and what happens here is we bring sub-base material in and we build the base to the contractor's requirements, and then we'll do all the testing on it. That's a metre square steel mould, and we'll put it in at the layer depths as prescribed, and we'll compact it to the level of density that's required to make it perform properly. This way we can start to look at what happens on a site, and we can look at the tools we use, like the various testing equipment Mark's highlighted, and you can see on the right hand side we're testing for compaction, for stiffness in the mould, and the mould's big enough to take out all the edge effects, so we're not restraining the material artificially, because it's literally tons of material that we're looking at in that mould. So that's one of the things we can do. So where you've got difficult materials to work with, even just a conversation with the guys at Sports Labs, that could help you out. Another thing we advocate, if you go into the next slide, Mark, is we're very keen on the contractor taking more responsibility for doing some checks on site. So this would involve, before even materials are transported, you do due diligence on the physical properties of the material, so the gradation and the physical properties as far as hardness and durability is concerned. And most quarries, if you're looking at crushed stone, will have independent laboratory certificates for their materials. So you should be able to get a batch of data from the quarry to check all these things before you even buy the materials. But also, where you're in a compromised area, or you think the materials, you're limited in your choice of materials, we also advocate taking in trial loads and then building small bays on site. It takes time. It's not ideal, but you can build a small bay with the material that you're going to use, to the thickness, to the density that you're hoping to achieve on site, and that can even be tested. It doesn't have to be tested independently. You can test it yourself with loads going over it, looking for movement or tracking, and using large, we call them bowsers, but tanks of water to see if it's draining. But that's another area that can help to alleviate some of the problems that Mark's highlighted in his slide deck. Next slide, Mark. Obviously, when you get to site and you start building the base, we've talked about all the tests that we can do, and the Mark's highlighted the ones that are significant. What we are seeing now is that because the industry is very subcontract orientated, and you have layers of companies coming to site to provide all the different services, so you may have a subcontractor who is doing your drainage and building your base for you. The main contractor wants confidence that what they're going to lay the artificial turf on is to standard. So we'll get put in the middle of that relationship, and then we'll be asked to sign off the sub-base, so that then when it's handed over to the main contractor to lay the artificial turf, there's a certificate in place. Now, we're not very good at regulating what happens when the turf goes down, because we're never there, but usually that's a good check and balance between the main contractor and the subcontractor. And the same goes for the different other properties we talked about of compaction or stability and porosity. So the testing is another tool you have. The next slide, Mark. So what we're trying to achieve, obviously, is and we're coming to wrapping up on the actual formal bit of the presentation. We're obviously trying to achieve a very flat, tolerant surface which is stable and durable. And next slide, Mark. what we've found is, as you know, there's a lot of good news about base construction, and it's not actually that difficult to get it right if you use the tools that are at your disposal. The good news is well-built bases last a long time. They should last at least 2 life cycles of turf. Many of the warranties I'm seeing for base construction are at 25 years. That would make your hair stand on end if you had any hair, like me. But you know, there are guarantees in place for the base will sustain for 25 years. It's a long time. The other good news is that building them properly doesn't necessarily cost more. It costs you much more to install a bad base than it does to install a good base. If you need to redo it, fix it, dig it up, put drainage in, that is going to cost you a lot more. It costs you a lot more financially, program-wise, and bad feeling with the client. You know, your best client is the one that gives you the refurb on the field you originally built. You're not having to do any marketing, sales. You know, that's the fantastic reference you want to get. So we advocate building better bases. So I think that's about it. If you go to the next slide, Mark. Yeah, so thanks for listening. There's a couple of other things we'd like to say. I'm sure there's some questions coming in on the chat. If there's not, I'll make a few up. Mark, don't worry about that. Next slide. We have got other resources, so if you're not got the information you're looking for from this webinar, you can go on the websites. We have a consultancy website that deals more with the design side of the artificial field construction. And if you go on to sportslabs.com, next slide, you'll see that we have some field notes, which is our little newslettery type technical journal that we do. And there's quite a lot of resource there on things about base construction and the way you can do key stage inspections or how to monitor things. So if you that's a resource that's there. You can just go onto it on the website anytime you like. And obviously we're around. You know, you've got our contact details, so if you want to ask any questions after the event or even, you know, down the line, and often we get 6 months later, we get a phone call, somebody says, oh, I remember you did that webinar, well, I've got a problem with my base here, can you help me out? So before we take some questions, there's just one area, Mark, that I thought we could just expand on, and I think it's really important because the market is very orientated towards renovation now. I mean, it's a very mature market. Artificial pitches have been around for a long time, artificial fields, and 50 years. We're seeing increasingly a large percentage of the market is renovations of old fields, and typically we would be commissioned to do a site investigation on an end of life field. When an owner or if a consultant's involved, when they're involved to try and put together a design package to refurbish it. We typically excavate holes from the surface down, so we'll dig trial holes to get right down to the soils, the subgrade, and do an examination of how the field's been built, what the thicknesses are like. But what are we looking for, in these scenarios? What are we looking for? We've got all these tools, we can do the testing. You mentioned a few things there. I think it's important just to emphasise with refurbishments, what are we looking at mainly identifying?
So as these fields age, they come across different conditions, especially with different climates. A field in Texas, for example, like West Texas, it might be affected by dust that is then, filtered down into the base. And this actually might be an example of one here, where, you've got a top layer that looks nice and clean. And as you dig in a little bit, and this is a field that's probably, 8 to 10 years old, as you dig down, you find it's all choked up with some fine materials there. and using these different methods of measuring drainage, we're able to kind of see where this water is moving, if it's even making it to the side drains, if those exist, and then you can come up with a plan on how to proceed with the install for, or how to specify later on what you need to make sure that the install goes well, and so that the field is protected for years to come. So we're looking at, when it comes to drainage, at least, we'll look at each layer, we'll dig down, we'll see what the composition is, see what the strata, if you will, of the whole of each layer, what that looks like, and sort of get a really good idea for what's going on. There's been a number of cases recently where we have tried to reuse a stone base, and like I said, it looks good on top, but you get down just a little bit, even a 1/4 inch, and then even beyond that, and you start seeing issues, and you don't want to lay a brand new field on top of that, because of course that problem is going to persist or potentially get worse depending on the materials you add in. So again, we talked about different infills have different properties. You're going to want to potentially readjust your plan depending on for your infill ratios or types of infill, depending on what's going on with what's underneath, and if you want to reuse exactly what's underneath, or if you want to break that up and add more material. But there's got to be a plan in place, and that starts with really rechecking what the existing base is.
Yeah, I mean, look, the designers will say to us, we need to have confidence that we can install a new field on top of that base.
Mm-hmm, mm-hmm.
Yeah. So, when we dig holes, as you said, we're looking at the material type to make sure it's suitable. It's still suitable, because it could be 20 years old. We don't know. It can be as old as that. And then we're doing testing. What are we giving the engineer? What do we do a site investigation report? We provide them with data that they can then use in their design. And the engineers have all got different ways of approaching these things. Some of them are using very sophisticated tools to do site investigations. Others are doing quite a soft or a light touch. But I think what I'm saying is we're advocating that you dig holes in these renovations, especially if they're fairly significantly old, and we're looking at like pitches or fields that are 14-17 year old, never been resurfaced, so they're very old. See what's there, and give the engineer or the consultant or the owner the information they need to properly refurbish that field. Just a quick one before we take some questions. You showed that the field that was flooded and all the organic material had washed out. How did they fix that field? How was that? Was that a sub-base problem, or was it just an infill problem, or was it just a storm that came through and caused a massive?
This one looks to be more of a storm that came through. This is sort of an example of, again, the any organic material is going to be pretty light. And it's going to move around a lot more compared to rubber or TPE or EPDMs. It's just something to watch out for. You might want to specify that for an organic field, you have a higher drainage rate. So instead of using a really tightly bound cap layer or a finishing layer, you'd probably adjust that and think about using a different stone that's maybe a little looser, still compact and stable, but a little bit looser to allow for a faster drainage. Considering that some of these organic materials, they're sort of like sponges, right? I mean, they're going to drain a little bit differently, and the layer below that the base itself will need to drain a little bit quicker to shed that water a little quicker. If you've got water that builds up in pools, or even water that moves around a lot, during heavy rain events, it's going to affect the field a lot differently. So there's other factors to consider when it's because it's an entire system. It's not just the base, but when we're building the base, we want to think about what's going above that as well.
Yeah, and I think it's very, very difficult to design for storms. Like, I mean, nowadays, I think the designers are looking at a 200-year storm event, which is occurring every other year now. So you design for a once in a 200-year storm event, and it comes along next year, and it washes out your field. In this case, it'd be really difficult to maybe design for that. But obviously, organic infill is much more mobile than perhaps some of the other infill materials. So yeah, I was just interested to see if that one was actually, because it probably is heavily contaminated as well. So we'd probably need to be lifted and cleaned, and who knows what's in that runoff water. Have we got any questions, Neil? I don't know if there's any questions coming on the Q&A from the...
Yes, Eric, we do. So the first one is about the slide deck being made available. That will be available within 24 hours, as well as a video recording, so people can go to the link and watch it in their own time as well. The second one for you guys is it's about response time to get to site. During construction, or if there's an emergency, what's the reaction? Obviously the guys are building projects at the moment, so that's from James. So basically the question is, what's the response time to get to site?
Mark, I think that's for you.
Yeah, we do our best to be available at the drop of a hat. Obviously there's it takes some time to make time in the schedule. But we try to be there. If you can do us a favor and give us sort of a lead time, or just be in constant communication, it makes it a lot easier for us. So if 2 weeks out, that you're going to be finished potentially between Wednesday and Friday of the following week or so, and just give us a heads up and just continue communicating. Then we can get you sort of penciled in on that date. And if something changes between now and then, or you're going to be delayed a day or two, just as long as we have just that constant communication, where it's just an email that says, hey, I know we said we were going to be done Friday, let's try and push that to Monday, then we can adjust. And because we're covering a lot of area ourselves, and a lot of different fields and a lot of different job sites. And so it's difficult for us, if you email us or give us a call at 6 o'clock on Wednesday, and we were meant to be there Thursday. Well, it's going to be difficult for us to adjust beyond that. So again, it's just, if you give us a heads up and we know a week, 2 weeks out where we kind of generally have to be, and then just continue following up, and then we can generally be there exactly when you need us to be. It's just that communication leading up to it. It really helps us out, and that way we can help you out a lot easier.
Right. I mean, schedules change, so and it's a dynamic situation, and you just try and you guys are on the road a lot because schedules change basically, and you're diving between one job and the other. But it all falls into place most of the time.
Mm-hmm. So the next question, guys, is from Sean, and he's asking if there's a set list of as I guess as a key stage inspections is probably what he's asking about. Now I know, Eric, we have that in Europe, and I've used that in the US before, so it's maybe worth discussing the different stages.
Yes, so this is a tried and tested approach with artificial field construction. So typically, it'd even start on the soils of the subgrade. You'd have a set of tests that would be taken on the subgrade materials, and then there would be a key stage inspection for subbase, which might involve, even as it's being laid, you may be in to sample the material to check that the gradation and the physical properties are as per the specification. And then obviously when the subbase is finished, there's a number of tests we can do at sign off, so we can do the porosity, compaction test, the planarity, stuff like that. So we do have a table, and we do have it's all laid out with when we're supposed to be in, what we're doing, why we're doing it, and how many tests we'll do on a platform of Subbase. So we can easily publish that. It's not, you know, it isn't unique to sports labs. It's in some governing body manuals on, you know, base construction and things like that. So yeah, absolutely could be provided to could put it on the website or something like that.
So another one from Jason. This one is, can it be built into the spec of the design? Maybe Jason's from an architectural background or a design engineer. So can these checks be pushed into the program of works?
Let's go to that one, Mark.
Yeah, absolutely. In fact, we recommend that, and we can assist with sort of designing that for you or along with you. It's good to specify that, yeah, you do have a planarity to 10 millimeter tolerance, or you do have a drainage rate to, you know, 25 inches an hour or something around there. And you can specify that, and we can hold everyone accountable, you know, down to the general contractor or the subcontractors to make that happen. That way, when we move on to the next stage, we know that that specification has been satisfied. And as you move on to the next stage of the project, you can be confident in moving to that stage, knowing that you've already checked off, okay, we do have a flat field, we do have a field that drains. So yeah, that's important. I think specifying that into every field you build is probably a great idea. It prevents problems down the line. You know, going back to, you know, if the field is down already and then you discover problems, well, you know, then the finger pointing that starts to happen, and things get messy. So if we just cut that part out and just start with, we specify this, and this, and we're able to check that off, then it just makes life easier for everybody.
Quite good timing on the next question. So Ruben's asked the question, what equipment in terms of contractors can they buy or use on site to prepare for an independent test institute to come? So I guess the accessible equipment, what's available for them to do their own site checks?
A straight edge bar, or even just a string line. I mean, if we can just check that off, just to kind of get a baseline there, so you know that you don't have a disaster to fix, you know, by the time that we come in and do our check. That can be really helpful for, you know, planarity, for example. I know there's also the box method that you can drag. Just really anything, any sort of a straight edge, you can do your own check on that, and then, like I said, we can come in and verify that and make sure that it's satisfied to spec. And then for drainage, I mean, that could be something as simple as running a hose along the base and just running the water, seeing where the water goes. Again, it's a pretty quick and dirty way of verifying that, okay, is this water draining vertically? Is it going where it's supposed to go? How fast is it moving in the direction that it's moving in? And then, of course, we can come in and verify that and produce an actual report, a third party report that says, all right, yeah, this field is in fact built to spec and does what it's supposed to do.
Thanks,
Yeah.
Mark. I think just on that, Eric, there is a contractor's set of equipment, isn't there, that is available, a set one case kit. So it's worth noting that as well.
Yeah, I think we can provide that sort of stuff, but yeah, I mean, a straight edge beam is like it should be in the engineer's car or in the hut or in the accommodation. And even running a hose, you know, you've got to make sure you run it for long enough, because you don't want to just check the absorption of the stone. You've got to make sure that it's actually flowing through the stone. So running a hose for, you know, 20 to 30 minutes before you actually look at any measurements, really important. Don't just put it on and say, oh, it's disappearing. It's just absorption you're measuring. So it's really important to do the basics, even just with a little bit of care. So that's just an hour. So we've basically run out of time. We don't want to be taking over everybody's day. So I think what we'll do is, if there's any questions that we haven't answered, Neil, and we know who's asked them, we can do an email response to them. First of all, I'd like to thank Mark for taking the time to put the presentation together and talk about his experience on sites, and Neil for producing it. Neil's got a very big gig tonight, so he's like 2 minutes, he's out the door. And thank everybody for attending the webinar. As I say, we like to do these things to try and, do a little bit of knowledge transfer and give you some tools that you can use going forward. So we'd love to have some feedback from you. If you want to get in touch, please do so. We'd love to hear from you. So I think that's about it. We'll say goodbye for now, and we'll see you on the next one.